Okay, so for this video, we're going to do a little bit of review of light, introduce the Bohr model of the atom, very much looking at the electrons and how the electrons interact with things. So let's start out with just a little bit about light. We know light is a wave, and we got this kind of wave, then we get the microwave. If we take a look at the distance from one crest to one crest, we call that a wavelength. And if we count the number of times that a wave passes a particular point, that is the frequency. We call the wavelength lambda, the frequency nu, but you knew that because this is a review. And we have the equation C is equal to lambda times nu, or the wavelength times the frequency, and C is the speed of light. So for all electromagnetic radiation, that C is the same, well, assuming it's in a vacuum. And we are going to take a look at a couple problems here. The first problem is, let's say I have a radio wave, okay? And I just went and I Googled the first radio station in Wichita that came up, and I got 97.5 megahertz. Now, mega is a prefix that we should be familiar with. Megahertz, that's a lot of pain, I know, okay. So, 97.5 megahertz is the same as 97.5 times 10 to the 6th hertz. A hertz is a 1 over a second. Now, if this is our frequency, okay, this is the frequency, what is the wavelength of this particular light? Okay, so I know C, because I can look it up. Sometimes I know it. It's 2.998 times 10 to the 8th meters per second. I'm going to round it to 3.00 times 10 to the 8th meter per second. And if I solve this equation for my wavelength, all I got to do is divide by nu, and I know that I have my wavelength is going to be equal to C over nu, which is equal to 3.00 times 10 to the 8th meters per second divided by 97.5 times 10 to the 6th 1 over seconds. You might want to put this in scientific notation, 9.75 times 10 to the 7th 1 over seconds. And when I put this through in my calculator, I get that my wavelength is equal to 3.08 meters, okay? Fairly simple. Now, we also can look at energy. Now, I'm not going to go through and review everything, but we do know that the energy is related to its frequency. The energy is related to the wavelength. Okay, for this one, we're going to look at the energy related to the frequency that we have here. Now, I'm going to erase this so I have room to work this. But to find the energy, we need to know Planck's constant, and we know E is equal to h nu. H is Planck's constant, 6.6 times 10. See if I can write. 6.626 times 10 to the negative 34 joules seconds, not joules per second, joules times seconds. And if we multiply that by 9.75 times 10 to the 7th, 1 over seconds, this is going to give us our energy, which in this particular case is going to be 6.5 times 10 to the negative 26 joules. That's a really small amount of energy, but again, it's the energy of a radio wave. Radio waves are very low energy, okay? Now, we also need to start taking a look at how the light interacts with electrons. And when we look at the Bohr model of the atom, it's going to be a relatively simple thing. Again, this is a model. If I actually were able to see an electron, I might be able to do more with this than that. Or if I were able to see an atom, but we're just going to use just a rough diagram. And let's say that's the nucleus. If that is the size of the nucleus, the entire atom is bigger than the wall that you see, or not just bigger than the board, bigger than the wall. But we're going to use this to scale. And I have electrons, and we say that they're in orbitals around here. And we kind of think about the planets orbiting the sun. When we have that, we have different energy levels. This isn't exactly the same way. This is just helping us to build this in our mind. And we can calculate energies with that. So I'm going to skip ahead to the calculations for that. And I know the energy of a particular level, which we're going to call N, is RHC over N squared. Okay, where N is the energy level. And RHC is a constant. It's the Rydberg constant. And the combined value of RHC, and sometimes you will see this with a negative value there, sometimes you will not. It doesn't matter. When you put it in there, this whole RHC term ends up being negative 2.18 times 10 to the negative 18 joules. That's what that value ends up being. So let's say I have an electron that goes from the third energy level and it jumps down to the first energy level. First of all, if it goes from a higher energy level to a lower energy level, it emits an electron. Okay, let's go a little step further. Let's calculate the energy of that electron. So I'm going to use this, if I take two energy levels and I subtract them, basically this is going to give me a change in energy, which is going to be equal to that negative RHC, or that value there, negative 2.18 times 10 to the negative 18 joules, times 1 over n squared for my final, and I'm going to do it 1 over n squared for my initial, and I can factor out this and just get 1 over n f squared minus 1 over n I squared. In this case, it's 1 over 1 squared minus 1 over 3 squared. And if I calculate that out, I end up with an energy in this case of 1.94 times 10 to the negative 18th joules. Now, knowing my relationship between energy and wavelength and frequency, remember before, now I'm going to erase the very bad model of the atom that I put here. And I know I have C is equal to lambda times nu, E is equal to H nu. Now, I can substitute this. If I solve for nu is equal to C over lambda, I can just substitute that in here. E is equal to HC over lambda. Or, rearranging this equation, lambda is equal to HC over E. Okay, so here's my energy. My wavelength is equal to H. C over my energy. This is at 18. And if we did this right, my units for wavelengths should come up in meters. And let's see, seconds cancel, joules cancel, leaving me meters. And when I do this calculation, I end up with 1.03 times 10 to the negative 7th meters. Often we want to convert that to nanometers. So if I take it times 10 to the 9th nanometers per meter, I end up with 103 nanometers, which tells us that this is not visible. Remember, the visible range is 400 to 700 nanometers. So this is how we can take a look at the Bohr model of the atom. I'll be doing another video shortly on quantum numbers and the electrons in the atom.